All right, so this is part 2 in the functional groups IR series, if you will. And so we're going to start off with prayer, and then from there, we're going to get right into it. Dear Heavenly Father, Lord, thank you so much for today. I ask that you please be with us as we continue this conversation about infrared spectroscopy and functional groups. In Jesus' name I pray, amen. All right, you guys. So let's get started. Today, we're going to actually talk about functional groups in greater detail, as well as discussing how to use infrared spectroscopy and how to interpret it. Okay. Let's see if this is going to work for me. All right, so an infrared spectrum interpretation is difficult as an arrangement of organic molecules is complex. So we can't use it by itself to interpret what a compound is, okay? Now there's programs and databases that can do that, but for an individual to simply just use it as a means to determine a compound, it is very complicated and difficult, and it's just not efficient. And so we use other types of spectroscopy in connection with infrared spectroscopy to identify an actual compound. And as you go through organic chemistry 1 and 2, you'll be learning all of these techniques. So one of the disadvantages of infrared spectroscopy is generally only used in pure samples. So if you have a mixture of compounds, that won't work. The compound needs to be isolated first. And then also, typically, we use infrared spectroscopy when dealing with small molecules. So when a compound is too large, too many functional groups, because of all the frequencies kind of overlapping, it typically doesn't work. So it's best to use with small molecules. Now, an advantage of infrared spectroscopy is it provides a unique identification of compounds, okay? So it does give unique spectra, and so that is it is an advantage. And that unique part of it is we call it the fingerprint region. So when we look at infrared light, if you guys remember, and I can go back to the previous slide, infrared light, as you guys can see, is in the range of about 4,000 centimeters to about 400 centimeters. Okay, so the frequency is 400 to 4,000. And so when you're looking at these numbers, I want you to keep in mind that all the numbers are going to be in between 400 and 4,000. And so from the 1,500 per centimeter range to the 400 per centimeter range, it is what we call the fingerprint region. And this is the region that is unique to each molecule. And so that fingerprint region can be used to identify unique molecules. However, again, you would use a computer software to be able to do this using libraries and such forth that would actually match it up. Now, for this course, we're going to be looking mainly at what we call the functional group range, which we'll talk about in a little bit, the functional group range. Now, we will use the fingerprint region, so don't get me wrong, don't completely ignore it, but a lot of what we're going to talk about is going to be in the functional group range. Now, the good news is it's not necessary to completely understand everything and completely interpret everything in the infrared spectra. It's not necessary. You can get useful structural information by simply being able to identify certain things in this in the spectra. Okay. Another advantage is that infrared absorption bands are similar among compounds. Okay, so if you know what the band looks like, they're very similar when you have the same types of functional groups. Right, so remember I was talking about a spring, a harmonic oscillator, all right? And so when you're thinking about this, it's kind of like a spring. You have your starting point, and then you have your endpoint. And so it oscillates. It's two atoms connected by a bond, okay? And remember we talked about those atoms, okay? And so in a vibrating bond, the vibration energy is in a constant state of change from kinetic to potential energy and vice versa. And so if it comes in, you're at potential, but then as it's moving, it's turning into kinetic, and then it pulls out potential, kinetic. So it's constantly going from potential energy to kinetic energy to potential, back to kinetic, just like a spring would. If you guys remember in physics, or if you're learning in physics, if you haven't gotten to that with springs, you have that same motion and that same movement as your bonds are vibrating. All right, so the peaks positions, and I'm not going to spend too much time on this, but I do want you guys to kind of understand this, is based off of some constants and some variables, okay? Or I should say some constants. The main thing that I want you guys to realize is that the frequency, which represents the band's location, because when you're looking at the spectra, your x-axis is frequency, okay, again, from 400 to 4,000. And so that frequency is based on the force constant as well as the reduced mass in kilograms. So there's only two variables. So only two variables are a chemical bond's force constants and reduced mass, okay? Reduced mass refers to M1 times M2 divided by M1 plus M2, where M1 and M2 are the masses of the two atoms respectively. So if you have a mass of one atom and a mass of another atom, you multiply those and then divide it by the sum of the two atoms, then you would get that, okay? That's a force constant. And pretty much what you're looking at is the fact that the main takeaway is because no two atoms have the same mass. That means all of them are going to have their own unique value. And because they'll have their own unique value, they'll all show up in different areas of the infrared spectrum because the velocity is going to be, sorry, not the velocity, the frequency is going to be different from one atom pair to another atom pair, okay? And this is why each chemical substance is unique, all right? So again, because this equation, which is what determines the frequency at which the bands absorb, and because no two things are identical, they're all going to have a unique spectrum. And this is why infrared spectroscopy can be used to identify functional groups present in a certain molecule. All right, so what determines the area of the frequency? Well, stronger bonds have larger force constants, okay, and absorb at higher frequencies. So if you look at this is just a general location. You have aldehydes, all right, which are going to be around 2850 to 2750 per centimeters, okay? And you will see that CH bonds are just a little bit higher. But then when you have your double bonds, your carbon hydrogen based on this double bond here, the bonds between the carbon and the hydrogen of the double bond is going to be stronger. I don't know if you guys remember in chapter 2, we were looking at these bond strengths. And if you notice, as the bond strength increases, so does the frequency. And so you have your arene, and then ultimately you have your alkyne here. All right. And so again, as the frequency, as the bond strength increases, the force constant K is increasing. And we also know that increasing S character in the bond. I don't know if I spoke a whole lot about that. I can't remember right now, but if I need to, I can do a refresher on that. But ultimately, all of those, as they're increasing, so is the frequency. All right, so this side is talking about peak intensity. So we know that there's going to be peaks there, but how strong, how far down, and when you look at the spectrum, you're going to see what a spectrum looks like. How does a peak intensity is determined. What causes it? Well, the difference in vibration, and also let me go back real quick. So you see how it says weak, where you can see here where it says weak here. When it's saying weak, that means that the peaks aren't very large, okay? Whereas some peaks are very strong. So anyways, the different vibrations of the different functional groups in molecules give rise to a bands of different intensities. So some functional groups have strong intensities, some have weak intensities. This is because the dipole, change in dipole moments with respect to each of these vibrations are different and they're unique, okay? Another factor that determines the peak's intensity is the infrared spectra is the concentration of molecules in the sample. And so you can actually have two different samples. If your concentration is too low, your peaks are going to be a lot smaller than if your concentration is higher, okay? So if you have a high concentration versus a low concentration. And I don't know if you guys remember, if you guys have talked about Beer's law in general chemistry, but you're going to see Beer's law again and again and again. And this is in reference to absorption and the relationship of absorption when it comes to concentration. Okay. Now the other two are constants, the absorptivity constant and the pathway is just how far is the light traveling. So those are constant numbers. However, because of those constants, you can actually use absorbance and concentration together to be able to determine concentrations based on how much light is actually being absorbed. All right, so another thing that we must take a note is the peak width. So in general, the width of infrared bond for solid and liquid samples is determined by the number of chemical environments, which is related to the strength of the intermolecular interactions such as hydrogen bonding. So what does this mean? This means that the more hydrogen bonding present, more compounds interacting with each other in solution, the broader the band, excuse me. And so things such as OH groups, okay, and NH, so nitrogen-hydrogen bonding, we know that those create hydrogen bondings, okay, right? Whenever you have an oxygen or a nitrogen, they create hydrogen bonding. So whenever you have those two functional groups, often you're going to see that your bond bands are broader, okay? And this characteristic is important when you're starting to look at different functional groups that show up in the same area. So even though you have a peak in the same area as something that you expect, if one has hydrogen bonding where one doesn't, if the peak is broad versus the peak being small, it will let you know what that functional group is, okay? So here you can see that there is intermolecular interactions going on here. And this is when you're dealing with OH groups. And in this case, we're showing alcohols. You see these R's? These are carbons connected to OH groups. Okay. So now we're going to look at the actual different regions. So if you remember, we talked about the fingerprint region, which is about 1,500 to around 400 or so. Okay. Now the region from 400 to about 2,500 centimeters, it really should be 1,500 centimeters. I need to fix that typo on there. You're going to see that they can be broken up. So how can we do this? So your area from around 1,500 to 2,000 is where you see your carbon double bonded to different atoms. So carbon double bonded to oxygen, carbon double bonded to nitrogen, carbon double bonded to carbons, okay? So you're going to see that stretch. Now, these are stretching motions, okay? You can have other areas that show these things up, but this is specifically dealing with stretching of these two atoms connected to each other. And then next here between 2000 and about 2850 or so, you have C triple bonded to nitrogen and C triple bonded to carbon bonds there, okay? And then last but not least, things that show up in this area are usually single bonded stretching motions, which is nitrogen to hydrogen, oxygen to hydrogen, and carbon to hydrogen. And that's about 2,800 to 4,000. All right. So let's look at the overall chart in the table. So here are some absorptions based on the different bonds. And again, remember it's harmonic. So you're looking at two atoms, okay? One bond between two atoms. And so you can see alkanes where they show up. You can see where alkenes show up and so forth. All right. And then I want to point out that when you have carbonyl compounds, okay, so carbonyl compounds, we have carbonyls. These are all carbonyls. However, they do show up at different times, okay, or different areas, different frequencies. So aldehydes, ketones, and then you have your esters, your amides. Your amides kind of show up closer to the 1700. Or a little bit under 1700, and then carboxylic acids are just above 1700s. But then carboxylic acids are not just carbonyl groups, you have your OH group. And so the OH group of carboxylic acid also shows up here, which is different than the OH group of an alcohol. Okay, and then of course alcohols have the OH group, but then they also have the carbon oxygen group that you're looking for. And so we're going to take time to go through a lot of these functional groups and reference to see what do they look like on an infrared spectrum. Now, we have a bit of a journey to go, you guys, so hang tight. We're about to be here for, for a while. This lecture is a little bit longer. All right, so we're going to talk about functional groups, and we're going to talk about them in reference to infrared spectroscopy. So first, we're going to start off how we started last section, talking about alkanes, okay? We're looking at hydrocarbons. So these are hydrocarbons that have only carbon and hydrogen bonds. And so alkanes, which have when there are no functional groups present, you're looking at carbon hydrogens and carbon-carbon bonds, okay? And so you're only going to see these two types of absorptions. Now, carbon-hydrogen bonds absorptions range between 2850 to 2960. So they're just below that 3,000 range. So if you see peaks just below 3,000, we know that there's alkanes present. And so one thing that I like to do is when I look at my infrared, I'll draw a line right at 3,000. And if all my peaks are on that side, in terms of all the quote unquote noise that you have, all the peaks that you have around that area are all on one side, then I know it's an alkane. Okay. And so then the carbon-carbon bonds show up bands between 800 to 1,300. So you're going to see some bands also in between 800 and 1,300. All right, so now let's talk about some other functional groups. And again, we're going from infrared back to functional groups and back and forth, okay? So as you guys remember, alkenes have double bonds, alkynes have triple bonds, and then arenes have the special bonds that are 6 membrane, and they're going every other double bond, single bond, and you guys can see the examples down here, okay? So when you're dealing with infrared spectroscopy, alkenes are going to have carbon-hydrogen bonds that are sp2 hybridized, okay? They are sp2 hybridized. And these are going to be responsible for peaks around 3,020 to 3,011. So they're going to be just above that 3,000 range. So just below 3,000 is alkanes, just above is alkenes, okay? And alkenes also have carbon, double bond carbon, and these are going to be around 1650 range. Alkenes also have some other peaks that you can see, some out of plane bending. So you have your stretching, which is the 3,000 area, but then you have some bending, out of plane bending that absorbs around 700 to 1,000. But the main ones I want you guys to focus on is the carbon hydrogen absorption and the carbon double bond carbon absorption, okay? All right, so next we have alkynes. So alkynes have the carbon, triple bond carbon. Now these are going to be a little bit unique because if it is internal alkyne, you're not going to have any carbon hydrogen stretching observed, okay? However, it is if it's terminal, because that carbon hydrogen is going to be present, then you're going to have some stretching at around 3,300. So it's a little bit higher than your other bands. But remember, they're still in the region where carbon hydrogen bonds are stretching. And as they go stronger and stronger, they go further over to the left. All right. So for alkynes, you're going to be looking for either both of these peaks or just one of them if it is internal. So let's see, what do these actually look like? All right, so the first one we have here is hexane. All right, this is hexane. So if you notice that all of the peaks on hexane are going to be, trying to get my stylus. All right, all the peaks on hexane are going to be to the right of 3,000. It won't let me do both. I can't zoom in and use it at the same time. That's fine. If you let me zoom in now. Yeah, no, they don't let you. Well, anyways, we can look at it this way. So you notice all the peaks are right below 3,000. And so we know that when that happens, it's an alkane and there's no double bonds present. Now, if we go over here and we look at the next one, notice with this compound, we do have some sp3 hybridization, and so we do have peaks below 3,000. But if we also look over here, we have a peak that is above 3,000. And so that's the sp2 carbon hydrogen stretching that you see there. You also have a peak here, okay? And that's that carbon double bond carbon. Now, if we look here for the last one, we do have some peaks here that are just below 3,000. We don't have any peaks just be above 3,000 because there's no double bonds here. But we do have a triple bond and it's terminal, meaning the triple bond's at the end. And so you have this hydrogen here. And so you do have sp carbon hydrogen stretching here. Hence why you have this peak over here around 3,300. And then you do have a peak here between 2,000 and 2,500 for your carbon triple bond carbon. And so as you can see, there's ways to being able to tell what each of these would look like. So next, we're going to talk about aromatic compounds. And so aromatic compounds do have the arene. And so because you have the arene, you have something that's a little bit unique to it. So you're still going to have your carbon hydrogen stretch that's just above 3,000 because you do have sp2 carbon hydrogen stretching. So you will have that, but it'll be a very weak stretch, okay? But you will have that. In addition to that, you're going to have some weak absorption between, well, you'll have some weak absorption between 1660 and 2000. We don't really pay attention to that a whole lot because those are both weak. We want to look at the medium to strong absorptions. And so with the medium absorptions, we have some around 1450 to 1600. And so this is where you're going to, when aromatic compounds, that's what you're going to look for. So let me show you what that looks like. So you do have some carbon hydrogen there, but the main thing that you're looking for is between 1600 and 1400 here. You're going to see what kind of looks like little claws, okay? So whenever you see peaks that look kind of very sharp and thin, and a lot of activity between 1400 and 1600. You're going to see a lot of activity there. When you have a lot of activity there, you think there might be a benzene ring. All right, so now we're going to move into some more electronegative atoms with carbon single bonded to other things, electronegative atoms. So first we're going to look at alcohol. We've already talked about alcohols for a little bit when we're talking about the hydrogen bonding. But again, as we know that alcohols are when you have an OH group that is directly attached to a carbon chain. And so you can see that here. You have your carbon chain. This is called isopropyl alcohol. We'll talk about naming a little bit more later. But you have a carbon chain. So these are carbons with the hydrogens, carbon hydrogens. And then here you have this red atom here. That's an oxygen. And then another hydrogen there. So you can see that that's there. Now, alcohols can be classified as primary, secondary, and tertiary. So if an alcohol is primary, if we have a carbon chain and the alcohol is connected to a carbon, so that's how you can write it this way, or we can do the Coca-Cola structure. You guys should be practice drawing these. All right, so we have carbon 1, 2, 3. Carbon 1, 2, 3. And so this OH group is connected to a carbon that only has one carbon attached to it. So this is considered primary. Okay? Whereas if I have a carbon that has an OH group on it, but this carbon here is connected to 1, 2 carbons, this is considered secondary. If I have a carbon that's connected to an OH group, and that carbon has one, 2, 3 carbons attached to it, this is considered tertiary. So again, alcohols can be classified as primary, secondary, and tertiary, depending on how many carbons are attached to the carbon that is attached to the OH group. Okay. Let me put this one in the right location. Okay, so we have an OH group attached to a carbon, and then you ask how many carbons is that attached to? An OH group attached to a carbon, how many carbons is it attached to? An OH group attached to a carbon, how many are attached to it to determine whether it's primary, secondary, or tertiary. Okay. All right, so a representation of an alcohol that you may be aware of is ethanol. And ethanol is the alcoholic or is the part of the alcoholic beverage that makes it alcoholic, okay? That's ethanol. You also may be familiar with ethanol when you go to the gas pump. You will see sometimes by your gas, it will say it is up to 10% ethanol, depending on where you live. Okay, so that's an example of alcohol. Another example of ethanol is ethylene glycol, and this is found in antifreeze, okay? And that's because its freezing and boiling point are very extreme. And so it stays a liquid for an extended area of temperature. And so ethylene glycol is another one that you may be familiar with. Last is propylene glycol. This is found in cosmetics and food products. And so propylene glycol is something that is also popular. Now, back to infrared spectroscopy. So again, we have alcohols. Alcohols are in that single bonded atoms, right? And so they're going to be close to the 4,000 range. And so specifically with alcohols, the OH group, you see a peak at around 3,400 to 3,650. And this peak is going to be very distinctive. It's very broad. I don't know if you guys remember, we talked about the reason why the broadness of peaks and the reason behind that. And so yeah, so that is your alcohols. Now alcohols or OH groups can also be found not just in alcohols, but also in phenols and carboxylic acids. And later on, we'll talk about carboxylic acids. However, with phenols, you're going to see that at approximately 3,500 centimeters per centimeters, okay? Now, in addition to the OH stretch, your phenols will also have aromatic bands. All right, so with phenols, because you have your aromatic ring and your OH group, you're going to see the band for the OH group, and you'll see bands for the arine group, okay? And now with carboxylic acids, we'll talk about that a little bit later, but they also do have OH groups inside of those. I can get my, here it is. All right, so again, because of the OH group, just a reminder that this peak is going to be broad, okay? It's going to be a broad peak. And with the OH group, that broad peak is going to be around 3,600. And with the alcohols, with the acids and the hydrogen bonding, they're going to be around 3,300. Okay, and even lower. All right, so again, this is the rationale behind it. We've already seen this. But again, that broadness is based on the hydrogen bonding within the molecule. Okay. Now, a free hydroxyl group, let's say that we had a low concentration and we had it in a solvent, such as tetrachloride, methyl tetrachloride. And so with this, because you don't have that hydrogen bonding, you wouldn't have that broad peak that you see with just a regular sample. All right, so this is, I wanted to show you guys exactly what does this look like. So here goes the IR of cyclohexanol. And so what you would see here is your broad peak here, okay? You'd have that broad peak right there. And that is your OH stretching. So you notice that this peak is broad and it's smooth. You see it's around the 3,300. Now this compound also, if I'm looking at this compound, these carbons here are sp3 carbons. So you also have this sp3 CH stretching. So all the peaks, there's no double bonds, are all going to be below the 3,000 range. So if I draw a line at 3,000, all the peaks that are in this cluster are below. So this means there's no double bonds. Now, alcohols not only have the OH group, but you also have this carbon here. And so you're going to also see this carbon oxygen bond here, which is going to be around 11, well, around 1,000 to 13,000, usually around 1,000 or 1,200. You're going to see that carbon oxygen. So just know every single bond in this compound is going to show different bands. And so all these bands come together to show you what cyclohexanol is. But you can, again, you see that functional group. And that functional group is indicative of an oxygen-hydrogen bond, which you see here. And then the carbon-oxygen bond, which you see here. Okay. So let's compare that with what we have next. All right, so next we're talking about phenols. And so with phenols, again, we have that benzene, that arene ring connected to an OH group. And so you have your alcohols, and you're going to compare that to what we have phenols. Now with phenols, all right, so because of this resonance, phenols are stronger acids than alcohols, okay? They're stronger acids than alcohols. And the OH group is sp2 hybridized. And so this gives some additional features with this, okay? So let's keep going. Okay, so I already explained that phenols are stronger acids because of that delocalization. The electrons are spread out, therefore stabilized there. Some examples of phenols is vitamin E, as well as O-phenolphenol, which is a disinfectant antiseptic. All right, so those are some common representations of phenols. All right, and so here we have an IR spectral of actual phenol. And so what you're going to do is you're going to still see this broad peak here for the OH group, but then what you're going to see is that activity between 1,400 and 1,600 that we expect, okay? And so you still have that as well. And so you have that. And then also you have that carbon-hydrogen bond. And so you can see this peak here. It's not labeled, but that's carbon-oxygen bond there. So whenever you see a broad OH peak and some activity there, you're able to identify that as potentially a phenol. All right. So next we're going to talk about ethers as a functional group. Now, ethers are similar to alcohols in terms of carbon single bonded to an oxygen. However, if you notice, in this case, instead of having a hydrogen on the other side of the oxygen, you have another carbon group. And so it's carbon, oxygen, carbon, and they're both single bonded to that oxygen. And if you guys notice, oxygen likes to be bonded to two things. So it still satisfies its needs, as well as allowing it not to be charged. And I'm just going to go ahead. I want to draw the lone pairs onto this as well, just so that you guys can see them. These oxygens would have two sets of lone pairs there, filling the necessary need for the the 6 valence electrons. But then because you have those two bonds, you have a total of 8, which gives you that octet full. And so ethers are another functional group that we're going to be looking at in organic chemistry. All right, so let's see a little bit more about ethers. So let me click here. All right, so some ethers that you might be familiar with is diethyl ether. And this is general inhalation for anesthetics. It's very flammable, it's explosive, and actually has serious side effects. I know a lot of people know that in terms of like knocking somebody out, which obviously we don't do that. But anyways, diethyl ether, which is the one, let's see, yes, here it is. So this right here is diethyl ether. You see diethyl, di meaning two, so you have two ethyl groups. And I know we haven't talked about nomenclature yet, but that's what diethyl ether looks like. You have dimethyl ether here, and then you have ethyl methyl ether there. If you notice, they have all very low boiling points. Also methyl T-butyl ether, MTBE, is added to gasoline to improve the efficiency of the combustion process. And so ethers, as you can see, are very flammable, and they have a couple of uses. Diethyl ether is very popular also in the lab when it comes for solvents, okay? All right, so now let's talk about diethyl ether, or talk about, excuse me, ethers when it comes for infrared spectroscopy. So in your ethers, you have that carbon-oxygen bond. And so if you remember, carbon-oxygen bonds are going to have stretching at the 1050 to 1150. I always say about 1,000 to 1,200 per centimeters. And this area has a lot of bands, and so it does overlap with other absorptions in that area. So you'll see often that your band is going to be a little thick and strong when it's a diethyl ether. And so you can see that here. So this is actually this infrared spectroscopy for diethyl ether. And so if you notice with diethyl ether, I'm going to draw the structure real quick on the thing for you guys. Notice there's no double bonds, so all the peaks are below 3,000 there. All right. And so you also have that carbon oxygen stretch there. And you see that it's broad because it's overlapping with other peaks. And so those are the, this is the peak that you're going to be looking for. And I just realized the structure was actually drawn right there. But that's fine. We have it twice. All right. So again, you're going to see that in between 1,000 and 1,200, you're going to see those carbon oxygen bonds. Diethyl ethers are pretty straightforward. You don't have a whole lot going on. All right, so next you have an amine. All right, so if you guys remember, amines is nitrogen, hydrogen that's attached to an R group. And so you can have an R group here. An R group is simply a carbon chain, all right? And then here could either be another R group if it's a secondary amine, or it can be a hydrogen there. But the main thing that you're looking for is with amines, you have that nitrogen hydrogen bond there. And what you're going to have when you do that is you're going to have a sharp medium intensity peak around 3,300 and 3,500. Now, NH groups, in addition to amines, you have amides. Now, we're going to talk about amides a little bit later, but if you guys remember from the last lecture, amides do have that carbonyl group on there. So we're going to talk about that a little bit later when we talk about carboxylic acids. So let's listen and let's look into more about amines, okay? So amines are derivatives of ammonia. And so with amines, so you see the ammonia structure here, you can have primary, secondary, and tertiary. Now, whether it's primary, secondary, or tertiary is dependent on whether it has one carbon attached to it. So this little block right here represents a carbon. So just like when we had our primary, secondary, tertiary alcohols, it's based on how many carbons are attached to it. And so with your alcohols, it was based on how many carbons were attached to that carbon. With amines, it's actually referencing how many carbons are attached to the actual nitrogen group. So it's slightly different, but similar. And so primary means that there's going to have one of these hydrogens replaced with a carbon group. Secondary, you have two of the hydrogens of ammonia replaced with a carbon group. And then tertiary has all three of the hydrogens are replaced with a carbon group, okay? So you need to be able to identify primary, secondary, and tertiary amines. Now, amines do act as Lewis bases. If you guys remember from chapter 2, Lewis bases have electrons that can be donated, okay? Electrons that can fill an empty orbital. And so ammonia, as well as amines, can act as Lewis bases. All right, now notice, because the primary and secondary amines do have hydrogen attached to them, they can participate in hydrogen bonding, okay? And so they can have that hydrogen bonding that we talked about. And you'll see in a second that the peaks that represent from those NH groups are a little broad, and that's because of the hydrogen bonding. All right. But first, let's dig in a little bit deeper of amines. So amines are functional groups that can be found in pain relievers as well as sleep inducers, okay? An example of an amine will be morphine. You can notice in the name morphine, I-N-E is ending in that name. That is actually extracted from the poppy. And it was actually used in Mrs. Winslow's soothing syrup. Okay, and that's morphine. Now, of course, we know that morphine is used for medicinal purposes for dealing with pain, especially for individuals who are on hospice. All right, another popular amines are nicotine. Okay, nicotine is an amine, and as well as caffeine. And nicotine and caffeine are mild central nervous system stimulants, and they're found in tobacco and coffee, respectively. Both of these compounds have cyclic amine components, okay? They all have cycloamine components. All right, so let's talk about the amines in terms of spectroscopy a little bit deeper. So the NH bond in amines is going to give a peak for every one that is present. And again, they're going to be between 3,300 and 3,500 per centimeters. And so primary amines, they have two hydrogens. And since they have two hydrogens, you're going to have symmetrical stretching as well as asymmetrical stretching. And so you're going to actually have two peaks that are going to be present. So when you look in that region and you see these two twin similar peaks, we know that those are amines. Now, secondary amines only have one peak. Secondary amines only have one peak because they only have one hydrogen. So remember, secondary amines have two carbons on them. And so they're going to have only one peak in that area. And then with tertiary amines, because there are no hydrogens attached to them, so that's an amine, and there's 3 carbon groups, and there's no hydrogens, there's going to be no peaks. So you can't really use the presence of that peak there to know that it is anything if it's tertiary. And so you would look for the carbon-nitrogen bond. So if you see a carbon-nitrogen bond present, but you don't see anything in the NH area, you know that that is a tertiary amine. But again, IR simply just lets you know the basics. You have to use other techniques to be able to also confirm other things. All right, so let's look at these in real life time. So the first one we have, notice over here in between the 3,300, and again, you see this is 3,299. We can round as long as it's in that general area. You see how there's 2 peaks here, there's 2 spikes. That's because it's a secondary amine. And then we also see that there's all the peaks, the other peaks are all below 3,000. These are some other peaks that are indicative of it, but we're not doing a whole lot there. But this right here is the NH2 scissor bending as well. All right, so here we have a secondary amine. There's only one hydrogen on that nitrogen group. And so if you notice here in this range, you only have one peak. You're not seeing those 2 teeth-like peaks there. Also notice that in this case, you have some peaks above 3,000, and that's because you have this benzene ring here. You also have activity in the 14 to 1,600 region, showing that benzene ring as well. And then there's some other things that are labeled that we don't have to take note of so much, but these are for like the fact that it's mono substituted benzene ring. And that simply means that there's only one thing attached to that benzene ring. But the main thing we're focusing on is the amine group right now. So with this one, again, it's aromatic. And so you have that activity here. Okay. But if you notice, there is not an NH group here. Because there's not an NH group here, it's because this is a tertiary amine. Okay, that is tertiary. All right, so next we're going to transition to our carbonyl compounds. And so we just finished all of our carbon single bonded to an electronegative atom. Now we're looking at our carbonyl compounds, which is going to be carbon double bonded to an oxygen. So again, a carbonyl is a part of the compound that is like this. Now, carbons have 4 bonds, and so of course this carbon has to be attached to 2 additional things, but the carbonyl portion of it is the C double bond O. All right, so carbonyl compounds are going to always have a sharp peak at around 1700. So if you see any sharp peak around 1700, plus or minus a few, 1670 to 1780, anywhere in that range, we know that there's going to be a carbonyl group there. The exact absorption of that compound is based on what type of carbonyl compound it is. And this is because of resonance and inductive electronics effects of the hydrogen bonding that provides a better understanding of infrared radiation frequencies. And so pretty much just know that carbonyl group is going to be in different areas based on what else it's attached to. So let's first start with aldehydes. So aldehydes are carbonyl compounds, and if you guys remember, an aldehyde is going to be bonded to at least 1 hydrogen. So if you find this carbonyl compound, and if at least one of these bonds has a hydrogen on it, we know that that's an aldehyde. Okay? Formaldehyde is a very popular aldehyde, and formaldehyde looks like this. So that actually is the simplest aldehyde available, and it actually has 2 hydrogens on both sides. So that's formaldehyde. Now, of course, for those who know anything about biological specimens or embalming, you've heard of formaldehyde. That's that lovely smell that you smell when you're downstairs in Cooper Complex by the gross lab. So formaldehyde is the simplest form of an aldehyde. So we also have glucose, which is a carbohydrate. And that is an important source of energy. So glucose is also a it's actually a version of an aldehyde. Okay. And so we can see that aldehydes can range in their characteristics. Benzaldehyde is also very popular. It's found in almonds. Now with benzaldehyde, if you actually crush up almonds, that odor that you have, that you smell, is based off of that benzaldehyde. Benzaldehyde is has a very distinct odor. Vanillin is also, which is pictured here, a popular aldehyde, and it's the active ingredient in vanilla. And so there's aldehydes all over the place. All right, so let's talk about the spectroscopy of an aldehyde. So aldehydes are around 1730 when they're saturated. And then when aldehydes are next to a double bond or an aromatic ring, such as you have here, you'll notice that the range absorbs at a lower frequency, and that's because of the resonance that can take place. So if we see resonance here, it can pop up, kicking those electrons up here. And so because of that, you'll see a lower frequency because those bonds are not as strong. Also, if there's a double bond, you can also get some resonance here. But here in this case, there's no resonance that can occur besides just those bonds kicking up and down. And so because of that, you don't have delocalization. And so therefore, it's going to absorb at a higher frequency. And so if you see a aldehyde that has a low frequency, but you also see the aldehyde peaks that we're going to talk about in a little bit, we know that it must be next to something with some conjugation. Now, let's look at this as an example. All right, so here goes a IR spectra of benzaldehyde. And so again, you're going to see in the 16 to 14 region, you're going to see a lot of activity. That's that benzene ring there. Here you see at around, this is 1696, so at approximately 1700, you have this sharp carbonyl group. And you're going to see that in all of our carbonyl compounds. All right. But also, aldehydes have something very special. That carbon hydrogen is going to have a stretch, and that stretch is going to create two distinctive peaks here. So aldehydes will always have a 27, about 27, 20, 28, 20 twin peaks. Okay, so we're always going to look for these twin peaks at around 28, 20, and 27, 20 or so. Okay, so 2800, 2700 twin peaks. And they're always going to look like two fangs. Okay. And so you always, if you suspect an aldehyde, look for those two peaks. The carbonyl peak is not enough. The number of the carbonyl peak is not enough. You have to also have that carbon hydrogen, because remember, aldehydes always have this hydrogen. And so you're going to see those peaks if it's an aldehyde. All right. Next, we're going to talk about ketones. So ketones have a carbonyl that's in between two carbons. And so you have a carbonyl group, but then on both sides, you have a carbon. Okay, and this is referred to as a ketone. A very popular ketone that most ladies know is acetone, which is nail polish remover. Okay, acetone, nail polish remover. You hear the O-N-E, acetone. That's relative to the name of ketone. Okay. Some other popular ketones is progesterone and testosterone. That's the female and male sex hormones. Again, you hear them ending in O-N-E. Okay. So let's keep going. All right. So ketones, saturated open chain ketones and 6-member ketone cyclists absorb around 1715. 5-member ketones are around 1750, and then 4-member rings is 1780. Now, the main thing that you need to know is that they're at around 1700. Now, the cool thing about ketones, the reason why you usually know if a ketone is a ketone is because it's not going to have any other functional group that's indicative of it being attached to something else. And so if you just see a peak at around 1700 and you don't see anything at 2800, 2700 for those twin peaks for aldehydes, and we're going to talk about the other carbonyl compounds, then you can usually confirm that it's simply a ketone. Okay, so the absence of peaks can also confirm something just as much as the presence of peaks. So here, again, you see this carbonyl peak at around 1700. Now, because this is a benzene, you also have your aromatic rings there. Okay, and notice that you do not have any peaks here. Well, I'm actually too far down. Notice you don't have any peaks here, and so we know that it is not an aldehyde. Okay, and that's because you don't have that hydrogen group here. You have a carbon here, and that carbon is not going to give you those peaks. Okay, let's keep on going. I think we're making good time. So next carbonyl containing compound that we're going to do is carboxylic acids. So carboxylic acids this time have a carbonyl group, and then on one side of them, you have this OH group. That is your carboxylic acid. And so there's going to be two main peaks that you're going to look for this with here. All right, so carboxylic acids are weak acids, but they're stronger acids than alcohols. All right, so carboxylic acids are the weak, strong acids of the organic world, okay? So they don't completely dissociate like strong acids do, but they are definitely stronger acids due to the resonance of the delocalization of the bonds when the hydrogen is removed. And so what makes a carboxylic acid a strong acid is that when that hydrogen is removed by a base, these electrons here can play in resonance. And that resonance or that delocalization that occurs creates this hybrid of a compound, which is stable. And because it's stable, it's willing to give up the hydrogen. Because remember, stability in organic chemistry has to do with, or I should say, the acidity of a proton in organic chemistry has to do with the stability and delocalization. And so because it's able to be stabilized, because of delocalization of these electrons, it's willing to give it up. Therefore, that hydrogen is very acidic. All right, some representatives of carboxylic acids are acetic acid, right? That's the active ingredient in vinegar. So household vinegar that you get is about 5% acetic acid. Lactic acid is also very popular. It's used in cosmetics, lotions, as well as it is produced by muscle tissue while doing vigorous exercise. So you have lactic acid. All right, so in terms of infrared spectroscopy, carboxylic acids have your OH bond, okay? And those are going to be at around, it's going to be a broad peak. It's even more broad than the alcohol peak. And it's going to stretch from 2,500 to 3,300. It's going to be a very broad peak. I'm going to show you guys what that looks like. And then, of course, you're going to have a carbonyl peak at around 1,700 again. So you're going to be looking for the peak that represents this and the peak that represents this OH group. So let's look at it. All right, so let's look at first butanoic acid. So if you notice this broad peak here, and it's very lumpy. And the reason why it's lumpy is because it's overlapping with other peaks in that area. And so you see these peaks here? These are the carbon hydrogen sp3 peaks of this compound. And so the broad OH group is overlapping and pushing those peaks down. And so because of the broadness of this OH group, because of the delocalization and the hydrogen bonding that's very high due to the two oxygens, relative to the alcohol that just has one oxygen on it, it is going to always be like I always call it an upside down mountain. So if you have a jagged, broad peak in that area, know that you're dealing with a carboxylic acid. And you can always confirm it because of that carbonyl group at around 1,700 that's there as well. Okay? And so you're going to be looking for those. Now, let's not get this confused. Let's look underneath at the 3-hydroxyl cyclohexanone. Just because you have an OH group and a carbonyl group does not mean it's going to be a carboxylic acid. They have to be attached to each other to create that delocalization. So if they're not directly attached to the same carbon, you're going to simply just have an alcohol group, which is a regular broad peak that's nice and smooth. And then you would have a carbonyl group as well. Okay, so again, they both show on the spectra, but the difference is when it's a carboxylic acid, they're attached to the same carbon and it's broad and it's jagged. Whereas if the OH group is somewhere else on the compound, it's going to be smooth. So let's look at that again. So an OH of a carboxylic acid is jagged, and an OH peak of just an alcohol is smooth. And you notice it's also not as broad. Right. Next, we're going to talk about esters. So what an ester is, and we have aspirin to show you. So if you look here, this is a carboxylic acid because you have this OH group. This is an ester. Because on the side where the OH would be, you have another carbon. So an ester is going to be a carbonyl group with an oxygen attached to it. And then on this side will be another carbon, not a hydrogen. And so these are esters. Now, esters are sweet odors, and they are responsible for the fruity smells of a lot of fruit, okay? And so they're what give all of these lovely things odors, okay? Also, they're responsible for the odors of flowers as well. And you can see some esters right here. Now, esters, when they're saturated, they absorb around 1735. They also have two strong absorbances within the range of 1300 and 100, and that has to do with the carbon. My screen just disappeared. Give me a second. That has to do, let me get my thing, because this right here has to do with the carbon oxygen. So this is the carbon double bond oxygen peak, and then the carbon oxygen peak is there. Now, when a carbon is next to an aromatic ring, it does absorb at a smaller distance. Or a smaller frequency, I should say. All right, so the next carbonyl compound we're going to talk about is amides. So with amides, you have a carbonyl compound, but you also have a carbon nitrogen that is going to be bonded to that carbonyl group, okay? So the amide is a carbonyl group, and then you have this carbon nitrogen bond on this side here. So, excuse me. So amide bonds are found in medicinal agents and proteins. Amide bonds represent in part for the 3D shape of proteins. So that's the reason why you have the bends and the twists and turns with proteins. A lot of that has to do with those amide bonds, okay? So in terms of spectroscopy, amide carbonyl groups are in the lower end of the carbonyl region, around that 1690, so just below that 1700. Now, amides are to amines as esters are to alcohols. So, as you can see, your alcohols, okay, have this, and then now there's a carbonyl group in the middle of it. So that's your ester. And then this right here is your amide. So you can see that similarity with those. Now, don't get confused, because you also call the conjugated base of an amine is also called an amide. So don't get confused. But again, we're not talking about that, and don't worry about that right now. But just know that it is called an amide. Now, the same way that amines could be primary, secondary, or tertiary, amides can be primary, secondary, tertiary as well. So a primary amine has that NH2. Well, the primary amide also has an NH2. A secondary amine has NH, okay? And a secondary amide also has an NH. And then tertiary amides, the same way as tertiary amines, do not have any hydrogens present. So guess what that means? Well, that means that it follows the same rules in terms of your NH2 peaks. So this is propanamide. And so you have that carbonyl peak here at around 1700. And then you also have this NH2, and notice how many peaks are there. You have those twin peaks. that are present there as well. Okay. And so the same way you have that stretching from each of those protons. When you're dealing with the amines, you have it also with the amides. The only difference is amides also have that carbonyl group as well. Okay. In the same way that tertiary amines don't have any peaks in that area, tertiary amides don't have peaks in that area as well. Okay. So in addition to those, we have a couple of other carbonyl compounds. These are the minor players. I also have an amide on here too. We already talked about this one. But in addition to amides, you also have acid chlorides and acid anhydrides. Acid chlorides have that chlorine group where that OH group was when you're dealing with carboxylic acids. We call those acid chlorides. And then acid anhydrides have two carbonyl groups that are separated by an oxygen. And so these are some other forms of carbonyl compounds. And then here goes an IR for that. So you would have your carbonyl group, but then you would also have a carbon-chlorine bond over there. Okay. And so we didn't talk too much about it, but alkyl halides do show up in that 600 to 800 range. And this right here is the spectra for acetic anhydride, excuse me. And so if you notice, you actually have two peaks that are in the carbonyl range, okay? And so both of those peaks represent the two carbonyl groups. And then of course you still have that carbon-oxygen bond because of this peak here that shows up, okay? And it's actually has two bands for those because you have that carbon oxygen from this side and then that carbon oxygen from that side. And so you notice with acetyl anhydride, you have two bands representing the two different parts of that acetic anhydride. All right, so let's do an example. Let's see if we can identify the possible location of eye absorption in the compound below. So when you're looking at this, the first thing that you're going to want to do is identify your functional groups. Okay, so let's do that together. So you have this here, which is a ketone. You have this peak here, which is an alkene. Or not this peak, but this portion here. And then you have this right here, which is a nitrile. Okay, so let's see if we can find those in this table. So ketones, if you remember, is carbonyl, and so it's going to be something around 1700. Because it's an alkene, you're going to have peaks just above 3000. And then your nitrile, you're going to expect a peak at around 2200 or so. Okay. Now you also have some sp3 CH stretching because of the alkane present. So you're going to also have peaks just below 3000 as well. So let's look at the summary of all of that. So you have, again, a nitrile group and a ketone group, as well as a carbon-carbon double bond. So nitriles, ketones, and then the double bond. And again, I mentioned the sp3 CH stretching as well. So now here's some IR practice. Let's see if you guys can look at this and figure out if it's A, B, C, D, or E. Take note that the chemical formula is given to you. So you should use that when you're trying to determine the answer. All right, so let's work it on it together. So carbon 5, so that means whatever the answer is has to have carbon, 5 carbons, 10 hydrogens, and 1 oxygen. Well, the first thing that I notice is I have a broad peak here. So that broad peak means that my compound has to have an OH group. Therefore, it can't be A, it can't be B, it can't be C. It has to be D or E. And so now I'm going to look at the chemical formula. Well, I notice that the chemical formula has 5 carbons. So let's count. 1, 2, 3, 4, 5. So that has 5 carbons. Let's see this one. 1, 2, 3, 4, 5. So they both have 5 carbons. Well, let's see. It has to have 10 hydrogens. So let's see how many hydrogens do these have. So this has 1, 2, 3 hydrogens on these. There's 4, 5, 6 hydrogens, 7 hydrogens, 8, 9, 10, 11, 12 hydrogens on that compound. So we know that that cannot be the answer. So let's just confirm how many hydrogens are on this one. Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 10 hydrogens. So this indeed would have to be E. Now, there's actually a fast way to determine what the chemical formula of something is, but we'll talk about that a little bit later in chapter 3. So let's look at the next one. So if I'm looking at this, I see C6H12O. I notice that all the peaks are to the right of 3,000. My little cricket line, but they're to the right of 3,000. And so because of that, I know that this cannot have any sp, it only has to have sp3 carbon hydrogens. So I know that much. I also notice that there's a peak here. That peak is indicative to a carbonyl group. So because it has to have a carbonyl group, I know it can't be this one, it can't be this one, it can't be this one. So I'm going to look to see, do I have 2 oxygens? Well, I only have 1 oxygen. Therefore, the answer has to be D. Because E has 2 oxygens. Let's go to the next one. Number 3. I'll let you take a stab at it. All right, so let's look here. Again, I noticed that they're only sp3 CH stretching. I notice there's no broad peaks in the OH range. And since there's no broad peaks, it cannot be A, it can't be B. I'm looking at the 1700 range, and I notice there's no peaks in the 1700 range. So it can't be D. And I also don't have any twin peaks in the aldehyde range. I'm just confirming. I gotta count my notches. So 11, 12, 13, 14, 15, 16, 17. Yeah, this will be the 1700 range. I don't see them there. And so next, I'm going to count. I have 6 carbons and 14. And so I have 1, 2, 3, 4, 5, 6 carbons here. 1, 2, 3, 4, 5, 6 carbons here. But notice that this one right here only has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. Whereas this one has 1, 2, 3, 4, 5, 6, 7, and 7 also on that side because it's symmetrical. So that's 14 hydrogens. So I know this has to be E. These are the type of questions that you're going to see. All right. So when I look at this, I see there's 2 oxygens, and then I also see this jagged broad peak. Do you guys remember what that stands for? So that jagged broad peak lets me know that I have a carboxylic acid. So it can't be A, it can't be C, It can't be D because that's not a carboxylic acid, and it can't be E. Therefore, it has to be B. And that is the end of our practice and our slides. So if you have any questions or any comments, please feel free to ask them in the chat, as well as I will give you guys some more practice on the infrared spectroscopy. Next class will be diving deeper into chapter 3 to talk a little bit more about the alkanes, and we're going to be diving into the individual functional groups of alkanes, looking at nomenclature and the properties of alkanes. So I will see you guys next time.